Well, we have now understood why ensemble is important, because we want to connect micro states with the macro states. So, we are looking at the atoms as the micro states, looking at their velocity, looking at their trajectory, and then taking a time average of all these parameters together as an ensemble average going into the time average. And we will discuss that, which is what we call ergodicity. Do not worry about the term, we will define it very, very clearly for you. But if you look at here now on your slide, we have now defined 4 ensembles. One is EVN microcanonical, where the energy is constant, which is called constant energy. If you look at canonical ensemble, which is isochoric, so in this case volume is constant, and we have temperature constant and number of particles constant. So, that is called canonical ensemble. Then we will talk about isothermal, isobaric. So, we are looking at temperature, pressure and number of particle constant. And finally, grand canonical, just to remind you about T, V and mu, which is temperature, volume and the chemical potential. So, which is the best one to do the molecular dynamics? So, it depends on the question that you are trying to answer, and that is very important. When you set up an experiment, the first thing you are going to ask yourself, what is the question I am trying to answer? So, let us say if I say I want to look at a melting transition, and I want to see and I want to see what happens to the potential energy. So, now I want to know what kind of ensemble should I be using. So, if you look at, I know that this is EVN ensemble, and I can obviously then change temperatures to it. So, microcanonical ensemble will be great for me to look at the temperature transition, because EVN will be constant, and I can essentially change temperature and see how these parameters are changing, how the potential energy is changing. As you know, the summation of potential energy and the kinetic energy will be same, because we are keeping E as constant. However, as we are giving more energy to the system, then we can see the change in potential energy. And what question we are asking is that if I go, let us say, from freezing temperatures and then go and heat the system and see what happens to it, and at what point it becomes frozen to a very cold surface or very cold temperature. That is one situation, or another one is reverse of that, which is called melting situation. So, in this case I may start with a block of crystal and heat it up and see at what point we can see transition, and how do I identify the transition. So, the driving force there again becomes potential energy. So, we look at the change in potential energy, and at certain point you see a jump, and that jump will represent the change in the phase. So, system will try to equilibrate for a long time, but when it reaches a threshold value, then the bonds are breaking and suddenly there is increase in potential energy while the heat is being supplied, and that goes to the latent heat of vaporization or with latent heat of sublimation. Any one of these situations that you look at, you are able to then traverse that and say, aha, at this temperature the melting transition took place, or at this temperature freezing happened. And those temperatures are important, because if you change the situation, thermodynamic situation, then you can also see, as I said in earlier session, if you put pressure on water, then it boils at much higher temperatures than 100 degrees Celsius. So, if I want to understand how the pattern works, and if I want to calculate some of these artifacts on the system, then molecular dynamics is great. I can go to the temperatures where it is so high that you cannot have a physical system available or stable in that temperature, like plasma state, which is very high temperature state. But I can do that on molecular dynamic situation. So, now in this case we are now going to look at MD results and the experiments. How do we connect the two? And those connections are the one which are very important here. So, let us look at them very quickly one time, and then what I will do, I will jump into a freezing and melting transitions. So, now you can see how we set up this ensemble, and this will be set up in an ensemble which is a microcanonical ensemble. So, remember that, because that is the situation where EVN is constant, we can vary the temperature and we can measure the changes due to temperature. So, now if you look at here analysis of MD simulation on your slide that we have seen earlier, I want to remind you that there are structural properties to look at, energetic properties to look at, and dynamic properties to look at. And if you look at structural property, energetic and dynamic properties are experimentally calculated. For example, X-ray diffraction give you atom positions, which is structural, temperature factors. It can also give me atom-atom distance. NMR can give me order, whether they are ordered or disordered. I can look at G of R, which is radial distribution function, and radius of gyration and density. Density obviously is one of the very commonly used phenomena. But now if you look at on the left hand side analysis of MD simulation, I can do property calculation using the trajectory of atoms like temperature, calculate pressure, and then I can calculate specific heat, how much energy I have to give to raise temperature by 1 degree Celsius under constant pressure or constant volume. Then I go to free energy, and we talked about several free energy systems like Helmholtz free energy, Gibbsian free energy, and they all connect to various kinds of transitions, and they are reactionary forces. So, now if you look at the heat of vaporization, that is where you are looking at the transition from water phase to the gas phase. And again, what we can look at and look at the processes, we are looking also at the processes like binding, folding, partitioning, etc. So, now let us take few minutes and set up this freezing and melting transitions, so that you understand what happens in EV and ensemble. So, I am going to now set up the experiment, and again this is experiment which was earlier done. So, essentially you are looking at a molecular dynamics movie which has been earlier produced. So, now let us go in here and let me make it larger. So, use the magnifier, we do not need this, we will set that up. Okay. Now, we go to higher magnification up to let us say 200. We can put this thing away. Okay. Now, you can see this whole situation. So, you can see EV and ensemble, and you have number of particles 1000, volume is 16,000 in reduced units. And if you really want to see some of the options, average for the movie, so we are going to look at the averages as they happen. And now we will start the situation. Let us see here. Okay, that's fine. Let's go here and do the averages. All right, so we are ready to do. Let me reverse it all the way to 0. So, this is in a gas phase, and we are looking at the freezing. So, in freezing, what we are going to see is reduction in the temperature as we go forward, and you will observe that. Let us take this averages and then start it. And I am going to let this move. So, you can see lot of energetic particles are moving around in the gas phase. Now, essentially reducing temperature. You can see the temperature curve here, and as you reduce the temperature, you can see that there are droplets forming. If you look at on the top here, the droplet 1, droplet 2, and but in between there is still some vapors, particles of the vapors what you can watch here. And as we go all the way down to, so let us stop here and also look at other parameter, potential energy. You can see a sudden drop in the potential energy at this time, which is indicative of the phase transition. And you can look at the pressure. Pressure is again is fluctuating, because in this EV and ensemble pressure can fluctuate, and we are not making it equilibrium. Total energy versus time, you are looking at the total energy going down of the entire system, and then if you look at temperature versus time, is the average temperature. So, it has gone down over a number of periods. So, let us move forward. If you look at here, these are the droplets, still liquid, but inside they are becoming freezing into a solid. So, you will see that the solid formation as we go further down. And this is now you can see completely freezing transition, where now you can see there are 2 blocks which have become solid. So, this is a very good indication of what we call its freezing transition. So, let me stop here and then we will look at another transition which is we call melting transition. Thank you.